Okay, we're going to do redox equations.
She's like,
All right.
practice your lyrics.
Redox is a short way to say oxidation reduction equations or reduction oxidation equations. The Re stands for reduction. The Ox stands for oxidation. Okay? So we call them redox for short. In general, and they have to occur together. You can't have just oxidation or just reduction. You have to have both of them occurring. Because oxidation is whenever something gives up an electron and becomes more negative, becomes more positive. So if it does that, there has to be something to accept that electron and become more negative. So they come in partnerships, all right? You can't have one without the other. You have to have together. This is a crazy way to remember the definition. Oxidation is loss of electrons. So oil, oxidation is loss. Reduction is gain electrons. Reduction is gain. Or you can do Leo, the line goes Gur. Leo, lose electrons, it's oxidation. Gain electrons, it's reduction. Whichever way. That's just a way to remember the definition.
I like oil rig.
Whichever way, I do not care how you like it.
Gain. I feel like that should be opposite.
Now, and this is actually the way I remember it. Oxidation means the species gets more positive. Reduction, the species gets more negative. That makes sense to me because reduction should be toward the negative side if it reduces, right?
Mm-hmm.
So oxidation gets more positive, reduction gets more negative. All right? So the first thing that we need to do whenever we do this, I'll show you some examples. And there's no good of memorizing common ones. I don't think that there's any good of memorizing. This is some examples. Chlorine usually becomes chlorine minus. That got more negative. So that means chlorine was reduced. Well, if it was reduced, why is it called an oxidizing agent? Because if it got reduced, it oxidized something else. So the term, if it has the term agent on it, it's opposite than what it does itself. Agent means what it does to something else. All right? That's kind of confusing to me. Why do they even need to have that terminology? But we do, and it's important that you know that. So here, since chlorine got more negative, it got reduced but oxidized something else. So it's an oxidizing agent. All right, let me go on to the next one. Oh, this is the page that skipped. Here, zinc got more positive, so it was oxidized, but it reduced something else. So it's called a reducing agent. All right? So anytime you have the agent on the end, it's what it does to something else, not what happens to itself. Does that make sense?
Yeah. Mm-hmm.
All right. Now, so whenever you have a reaction, you have two, if it's a redox equation, you have two things occurring. You have one thing being oxidized, one thing being reduced. There are some equations that are not redox. If none of the oxidation numbers change, it is not a redox equation. Let me say that again, you might want to write that down. If none of the oxidation numbers change, it is not a redox reaction.
Can you say that one more time?
If none of the oxidation numbers change, it is not a redox reaction.
And you said there were two things that made a redox equation?
If it's oxidized and reduced, it's got to have both.
Okay.
All right. Now, so that means that we have to be able to assign oxidation numbers. All right, so look at this equation. This is just a simple synthesis equation. This is one everybody should know. You should be able to balance it by yourself pretty easy. Here's K, here's Cl, and it gives me KCl. K by itself has a zero charge. That is potassium metal. That's not potassium ion. If it's a potassium metal or a potassium atom, it can't have a charge because all atoms are neutral, right?
Mm-hmm.
So this has a zero charge. Here, chlorine also has a zero charge. It's a molecule, it has a zero charge. But over here, where they make a compound, potassium is +1, chlorine was -1, it equals 0, that's why it was KCl, right? So that's a +1, that's a -1. If I break that down into its half reactions, and half reactions means you take one element and what it makes, and then the other element and what it makes. Those are the two halves of this reaction. So if I take this part and say K made K+. So it was plain K with a zero charge here, made a K plus over there. That charge changed, didn't it?
Mhm.
So automatically I know this is a redox equation. Cl was a zero charge, and it made Cl minus. So that charge changed, that's a redox. This one got more positive, so it is oxidation. This one got more negative, so it is reduction. That's pretty easy, right? Okay, so whichever one got more positive is oxidation. So this is our oxidation half reaction. This one got more negative, it is our reduction half reaction. Now, I want to show you what happened. All right, in these reactions, the charge have to equal the same on both sides. Notice I didn't say they had to equal 0. They have to equal the same. This one, this side is 0. So for this side to equal 0, I have to add an electron, which makes sense because K gave up an electron to become K plus. Does that make sense? This one, this is 0. This is a 2 minus charge because there's 2 of them. So this one had to gain 2 electrons in order to be 2 Cl minuses. Does that make sense? Notice that the electrons are always on opposite sides. Here, the oxidation number will always be on the more positive side. Well, actually, the electrons are always going to be on the more positive side because the electrons are negative, right? So here, the more positive side was the product. Here, the more positive side was the reactant. Okay? So I just add however many electrons I need to do this. Now, the thing about redox equations is that the electrons for this to gain had to come from this loss. That means this needed 2 electrons because there were 2 chlorines. Everybody agree with that? I only put 1 here. So I'm going to have to multiply that by 2. That's why when we balance the equation, there's a 2 in front of the K and 2 in front of the KCl. Because I had to multiply by 2. I wouldn't do that. I wouldn't balance it that way. It's so much easier to balance just by inspection. But there are some more difficult ones that you have to balance the long way. All right? So that's why this one, I end up multiplying the K by 2 and all that kind of stuff. Now, so in order for us to find out if it's redox or not, you have to assign oxidation numbers. And you have to assign oxidation numbers to everything. That means that even on polyatomic ions, you have to figure out what those oxidation numbers are. So what we're going to do first is spend some time doing oxidation numbers. This is on page 17 of your notes. This is important. You might want to put a star beside it or highlight or something like that because you need to be able to figure out what they are.
The rules.
These are rules. And they're rules that are pretty easy. It's not like stuff you're going to have to really memorize. You should already know it. All right, first, the oxidation number of element that's uncombined, in other words, a free element is always 0. If it's just copper, if it's just iron, if it's just sodium, that charge is automatically 0. If it's the atom, all right? Or if it's the molecule, like in the case of a diatomic molecule. You should already know that. The sum of the oxidation numbers of a neutral substance equals 0. Remember when we were doing compounds, how you had to make them equal 0 before you could name them, write the formulas?
Mhm.
That's what it's talking about. So you already know that. In an ion, the sum of the oxidation numbers equal the charge. So if I'm doing NO3 minus, then when I add these up together, they don't equal 0, they equal minus 1. If I was doing NH4 plus, when I add those up together, they have to equal plus 1. I don't want them to equal 0 because they're ions. Does that make sense? So if you're doing an ion, it must equal the charge of the ion, not 0. All right? And some elements you just got to know. Group 1 is every single time positive 1. They never change. Group 2, every single time positive 2. They never change. Fluorine is always negative 1. That's the only one in that column, by the way, that is always negative 1. Most of the other ones are most time negative 1, but that one is always negative 1. Oxygen is almost always negative 2. There are some situations, and there's one in this practice where it's not a negative 2. Most of the time, though, it's negative 2. It will be a negative 2 unless one of these other ones come into play. All right? Hydrogen is almost always positive 1. I have seen hydrogen be a negative 1 because, remember, hydrogen can either lose or gain that electron. So it can be a negative 1, but sometimes it's not.
I thought hydrogen was in group 1.
Hydrogen is in group 1, but hydrogen is one that can change, that can move. Remember, matter of fact, some of the old periodic tables has hydrogen in group 1 and in group 17. So some of the newer periodic charts has it completely separate. But hydrogen, because it's only got one electron, it's just as easy to lose one electron as it is to gain one electron. So it's kind of half and half. But usually it is most of the time positive one. All right. And the last one, in binary compounds with metals of group 17, they're -1. So that means that if it's a binary compound with any metal, then you can count on 17 being -1, group 16 being -2, and group 15 being a -3. Okay, that is if it's in a binary compound. It doesn't work if it's in a polyatomic ion. That's going to change. All right. So let's look at this example. And I don't really do it the way he does it, but some of you it might make sense. All right. So I'm going to talk about this one right here on the board.
Can you zoom in?
I can. I think it is. Is that better?
Mhm.
Okay, so if I'm doing K2CR2O7, all right? So I'm going to basically follow these rules, and again, I wouldn't take the time to memorize them. Things kind of work out. So we know that in general that K is always going to be a +1, right?
Mhm.
Okay, so if I say +1 times 2, that's my K. Everybody agree with that? All right. Now what I do is I usually do my first one or my last one first, and I save my middle one for last all the time. Because your middle one a lot of times is going to be one of those elements that changes. It's either going to be like nitrogen or phosphorus can be a positive or negative, or it's going to be something in that middle section that can have more than one oxidation number. So I'm going to now jump to this one. Okay, and I'm going to say this is a 2-. There's no reason for me to think that it's not a 2-, it's not breaking any of the other rules. So I'm going to assume, since most of the time oxygen is 2-, I'm going to assume that it's 2-. So if I say this one, that is 2- times 7, right? So this equals a 2, +2. This equals a -14. Does everybody agree with that so far?
Why did you skip the CR?
I'm going to save it for last because it changes. CR is one of those elements that's in the transition metals that can have more than one oxidation number. So I can't just figure out what it is.
How would you know to not do that?
I almost always save the middle one for last. Do first one, last one, middle one, if it has a middle, yes.
How do you know if oxygen breaks the rules and it's not a -2?
It's going to usually do something weird already. Like right here in this one, oxygen breaks the rules because K's got to be +1. So that means oxygen here has to be a 1/2. Because if there's 2 of them, and 2 of them have got to equal the same as +1, then it's got to be something different. So there's usually one of those other rules in front of it that makes sense. If you're not sure, try plus a -2. You'll usually figure out if that's right or wrong very quickly. Because it won't work. Like it wouldn't work if you put a 2- there. Because if I put a 2- here, that means K would have had to be a 4, and it would have been impossible. Okay? So now what we got to do is we got to figure out what CR is. Okay? So right now, if I do this right now, I have a 12+, right?
Mhm.
Or 12+ is what I need, right?
You have a
I have 12-. So what I need is a 12+. Everybody agree? Because I want it to equal 0. Does everybody agree with that?
Mhm.
Okay, so notice that I have 2 CRs. If I have 2 CRs and I need a 12+, what must one CR be? A 6+. And let's put it in our formula and see. 6+ times 2. So this should be 2 plus 12 equals 14 minus 14. It equals 0. That's right.
So they're always going to equal 0 at the end.
If it's a compound, like this one right here, see that's a positive charge.
And so it's always
If
gonna
it's a compound, they always equal 0.
it's always gonna give us the compound and then tell us how many of each element.
For
there
this
are
part,
in
yes,
it.
yes, yes.
Okay.
How'd you get 6+?
All right, because I knew I needed a 12+. All right, so this all together has to equal 12+. I have 2 of them, so I used half of it.
Can you look at like the element and like know what it can't be?
Most of the time, yes. But in the transition elements, they're called transition elements because they have more than one oxidation number. Or remember how the ones with Roman numerals, like nitrogen, phosphorus, and things like that, if they're negative, they're always -3. But if they're in the positive place, then they're going to have something freaky. Like I've seen nitrogen have all the way from a -5 to a +5. So like 6 different answers. So you have to, there's some of them that you need to say for last. Yes,
Is it always gonna be the first two added together equals the last one?
yeah, usually what I do is this one and this one will equal this one, except for the sign will be opposite. Now, and sometimes, like right here in this practice right here, except I've only just do 2 elements at a time. It gets more complicated when you add a third, okay? But what I want you to do is I want you to try these right now. And literally, you're just gonna go through and see if you can figure out the oxidation. You can write them above them or you can write them out to the side, but I want you to try that right now. And you may want to stop videoing mine. We'll practice.